So I want to talk to you guys about scaling live OTT with Dash. I gave a presentation at DMUX around scaling ad insertion in OTT, and a lot of folks talking about how we actually scaled Dash to begin with. And I wanted to go back to a previous presentation and just kind of update it and give the information out again. I guess I'm Zachary Cava, so I'm over at Hulu. That's Rubber Ducks. Rubber duck debugging. I like talking to myself a lot, so it helps. It's great. Like I said, I'm at Hulu. Hulu, 2.5 years ago, we launched a live TV product. We'd classically been in the streaming video on demand, and before that, free video on demand. It's been quite the progression of product life cycles. But this live TV product is meant to be a replacement to that cable bundle, right? You get your local live channels. You're also going to get your premium, or you're going to get a DVR that's going to follow you across all your devices, and you also get access to our full VOD library. So you can watch all the next day library content as well as those live linear channels. From a technical perspective, it's actually a fairly big system. So we have thousands of live channels that are coming in constantly. That is due to the fun thing in the US, which is called affiliates. Every major metropolitan area has their own version of Fox, NBC, ABC, and CBS, as well as a couple other ones. And each of those get unique streams, and you get to ingest those and distribute those to all those users in that area rather than a national stream. We actually do not do the acquisition and encoding for those streams. We use our encoding vendors for that. But after the encode is done, we get that into our internal systems where we're running packaging and encryption and then down to the client via manifest and playout. On the client side, we actually own most of the players. There are a couple of proprietary players we have to operate with. But this gives us a lot of flexibility in being able to kind of tweak that last mile delivery pretty substantially where we need to, and innovate and hopefully bring back solutions to the larger community where we can. And so the last part I would say is to phrase this, to frame this talk is like the majority of our usage is in the living room. This is the 10-foot experience. This is where you're sitting back and you're leaning. We don't actually have the majority of experience on mobile or on your desktop. And the downside of this is the things that people don't upgrade are their living room devices. They buy a TV and it's their TV for 6 or 10 years. They buy a streaming stick and that's their streaming stick until it lights on fire. And so the hardware in this ecosystem varies very widely. You can have a very, very powerful game console, but you can also have a device that you're not sure how it boots. There's no CPU, there's no memory. And you need to run a full app experience across these devices. And when it comes to streaming, it can be very challenging. And so today I just want to walk through how we went about taking live Dash and streaming live content with it, the problems we encountered and how we went about optimizing it with Dash mechanisms, where that didn't work and how we expanded, and how we're brought that back to the community to help everyone do it themselves. And so live streaming with Dash. Now, a lot of folks, the first thing they ask is, why didn't you use HLS? Everyone's using HLS. That's great. I'm happy that you guys are using HLS, but Dash is something that we've used internally at Hulu for a long time because it works really well in VOD for ad insertion. The ability to model multiple assets within a single timeline, irrespective of what are contained in those assets, was a very powerful concept. And when we came to live streaming, we wanted to continue to embrace Dash because it actually has a great property that is overlooked, and that's the timing model. The timing model is something that exists in Dash. Unlike HLS, where it's a list of segments, there's actually an explicit clock that can be applied to the presentation that's going on. In particular, this clock allows you to model the assets either synchronized with the real time or synchronized with a fixed point. Right? It depends on whatever your use case is. Event streaming is a fixed point. 24/7 live stream, likely going to be wall clock. This means that every segment within that timeline can have an explicit availability window. This allows you to announce things into the future. This allows you to remove things from the past, but at a very fixed rate. And as long as you can synchronize your players, which using server time is a better thing than the client clock, you can actually ensure that clients are discovering streams at the same time. The other great part about this timing model is that it's very configurable. Everything that you're doing with everything you can configure is within the MPD's attributes. You can define how much of a buffer you want to be able to seek back into, how much delay you want off the live head. There's quite a bit of attributes. Maybe there's too many attributes, but there's a lot of attributes. And it's very powerful. So and then in typical live streaming, right, you need to update because new segments are becoming available. Wall clock is moving, new things become alive. HLS, this is just a simple update. You add segments at the end. Dash, you can also do that method. But because it has the timing model, there are more advanced ways you can extend it. One way is to have the player naturally discover segments without getting updates. And that's because of the rigid timing availability and understanding of the segment, or the segments within the stream. The other way is with in-stream updates where the segments themselves are carrying description updates about the manifest. I've actually never seen that implemented in a player, and we'll talk about why we didn't do that in a little bit. But the timing model is a very, very powerful component of Dash, and if you're having trouble aligning multiple assets, I implore you to look at this because it will help you very, very much. But now that you have a timing model, well, you need to get those segments available to the client, so you need to actually address them out. Now, you can do a list of segments. I do not recommend doing that because it's just a lot. So the great thing you can do is templatized addressing. And you could do this in multiple ways. One way, you can provide a template, and if your stream is well-formed, all of your segments are the same duration, you're in a utopia that exists somewhere, I believe, you can just have that template and a counter. And the counter goes forward, you have a new URL, you can download it, and everything is aligned within the timing model. And that's great. Now, again, I believe that's a utopia that exists somewhere. I unfortunately don't live there. The streams we have actually have a lot of variation in the duration, and this comes into the fun thing called non-integer frame rates. I'm not going to go into that too much. But the other side of it is if you want to make sure that when you seek, you're reducing the amount of time on seeks as much as possible, you want explicit addressing to avoid splay in the timeline versus like where you're guessing that you're going to seek to. And so you can explicitly address segments by listing them out directly. And that gives you that, and so you can combine that with the templatization to bring together the whole stream. And you could do either time or number. There's a whole war about it. No, I'm just kidding. No, you could do time addressing, which is the addressing of the time, the availability time of that segment. Sorry, no, the presentation time of that segment. Or you could just do number as if it was the duration, or if it was the non-explicit timeline, but the number is actually mapped to an explicit segment. We, in production, deployed $time, which is actually, as I found, apparently unique. But we did this because of restrictions on our ingest systems. There was not actually a lot of statefulness to begin with, and because of that, we had to carry through a consistent view of the world, and the only way we could do that was with time, not with numbers, because we didn't have anything that was keeping track of that number in a very good way. And to be honest, we're reevaluating this in low latency, because when you're doing low latency, you actually want to be able to predictively grab the next segment. And if you don't know the duration of the current segment, because it's still being published, it's very hard to start the request for the next segment. So that's just something to be aware of if you're taking your first look at this. Now, the other thing that is fun and easy to do, multi-CDN enablement. Instead of producing the same list 3 times, you can actually just throw in multiple base URLs. And the player can be implemented such that the ABR uses that as a select to jump between the different segments. Now, this does mean your CDNs need to have a consistent picture of the world. If you do have different versions of the stream being published to different CDNs, I would not recommend this. I would recommend separate manifest or separate adaptation sets. But the biggest problem here is segment authentication. So a lot of people, if you have premium content, you cannot have segments that you can just arbitrarily download. You need to have authenticated URLs. And in order to do that, you need all of the CDNs to either respect the same authentication scheme, which, spoiler, they don't, or you can just attach all of them for every CDN and have a very long URL, which does work, I can tell you from experience, and just configure all the CDNs to ignore the other one's authentication scheme. It's not great, but it works. The other thing is, if you are doing per user tokens, you can actually abstract those tokens out of the manifest using a thing called XURL query info, which means it allows you to say, hey, I'm putting the tokens in the main manifest URL. They're not going to be in the body. Make sure to reattach them. And I talked a bit about that at DMUX as well. But that's the basic components. I didn't go into periods too much here, but like those are kind of what you need to start out with a Dash live stream. So I want to look at what that gives you. If you take your new device, or you take your new system, you get it out of the box, don't use any of the configuration parameters, and you set up a live service, what are you going to get, right? Now, for our streams, we actually do multi-period, and we're going to ignore it in this example just because there's not enough room. We have 8 video representations from up to 720 at 60 FPS, or 5994, sorry, non-integer frame rates. One audio representation, the 608, 708 captions are in the video frames, and we use 3 segment CDNs. So if you take all that, you say, great, I've got my out-of-the-box manifest generator. What's the manifest look like? And you go, cool. You can start out, you've got your MPD, period start, base URLs, start the adaptation set for video. And then you keep going, and going, and going, and going. Hey, wait, hold on. We got to the next representation. Remember, there was 8. And then many, many moments later, you get to the end. 36 slides later, exactly. And it's kind of depressing, but like this is what you get, right? If you try to use something out of the box, you're going to likely need to do a little bit of tuning. In particular, so it's around 700 XML nodes. That's 46 kilobytes uncompressed. That's pretty big. It's 30 milliseconds of parse time on a moderate laptop. This is not a streaming stick. This is a moderate laptop. And this doesn't scale. In particular, it doesn't scale as you're trying to add features to a product experience. So if you want to enable something like full program lookback, say for a 4 or 5 hour sports game, Wimbledon is 12 hours programmed on networks. That thing is ridiculous to stream. But this just doesn't scale. So at 1 hour, you're at around 8,600 nodes. At 3 hours, you're at 26 and at 2 megs. That's basically downloading another video segment for every manifest update. And that's a little insane, right? And so what makes this so big, right? You're doing explicit addressing. That's obviously going to be one big thing there. And the other part is multiple periods, because multiple periods mean you have to redeclare representations, adaptation sets. It's not just a simple addition of another segment. But there are actually ways to optimize this just within the Dash spec. And so I would say do not deploy at all what I showed you. Also consider these following things, right? And so the other side of it is like, why do you want to optimize? Well, when you're streaming live, concurrent challenge, you have all of your users needing updates all of the time. And as those updates are getting bigger, it's too much processing power to be generating them for every user. And so you need them to be cacheable. And in particular, there's 3 pieces you can optimize. You can optimize your server generation, you can optimize your network transmission, and you can optimize your client. We decided to focus on the network and client because we're okay with burning a little bit more money, not a whole lot, a little bit more money to get something out the door, whereas the network and client are very fixed. They're out of our control for the most part because there's such a wide variety you have to operate in. And so we need a high cache hit ratio. We need to minimize the cost of these updates. And yeah, sorry. Cool. So let's take a, oh, wait, yeah, sorry. Again, end of the day. One thing I want to call out is it's important to optimize holistically. Now you could say, why didn't you just gzip your response? And that's a very valid thing, and that is actually very crucial feedback I got from somebody on HLS. Anyhow, the problem though is you're now trading client computation time, right? That manifest was very big and took parse time. If I gzip it, I have to unzip it and then parse it. And that's double the operation time. And so you can, but again, you can simplify this a little bit. First thing, you can actually just say repeat this segment. So when you actually have consistent durations or multiple segments in a row, you can collapse them together. Super effective. It's not effective on pattern durations, which again gets to non-integer frame rates. But that's, we could talk about that a little bit more. You can also omit the t-values, because the t-value is implicit of the next segment. You only need to have a t-value, which is the presentation time of that segment, when there's a gap or when you're at the start. And so this just lets you clean up and not actually provide a lot of redundant information, because the player has to calculate this anyway to abide by the timing model. The other thing you can do is you can take that segment timeline, which is typically in a representation, and pull it to the adaptation step level if you have aligned streams. This is not a given. If you might want to check your vendors, because I've actually seen most that don't provide aligned streams. We had to work very closely with them to get this. But if they are aligned, you can pull them up. One minor note there is if you have 30 FPS content and 60 FPS content, typically those are encoded at different timescales. Timescale also has to be aligned. I would recommend 90,000. Very good timescale, very, very good arbitrary number, and it comes out from, I think, Kilroy. But this is really good. This gets you pretty collapsed. And so if you just apply that to that same 5-minute manifest, you can kind of fit it on one slide if you make the font a little bit smaller to cheat. But it goes from around 7,000 or 8,000 nodes to 78, which is great. 8.1 kilobyte uncompressed size and 20 millisecond parse time, and that's good. But it's just reducing the magnitude, right? It's not addressing that long-term scale problem, right? So at an hour, you're still at 700 nodes. At 3 hours, you're still at 3.4. And so it kind of gets you there, but you're still getting fairly high. And your cost is accumulating over time because you have more information to present. As you have ad breaks, as you have program changes, you have more information in the stream that you need to convey. But then the question is, what is really changing across these updates? So on the left here, I have one point in time. On the right, I have the next point in time that I got an update. Can somebody in the back see the difference? Or anyone in the front? It's very hard to see, yes?
The number of repeats changed?
Yeah, exactly. The number of repeats changed, and we added another segment on the audio timeline because it was a little different. And I'm amazed you saw it at that close of a distance. That's great. But that's the only change, right? There's 2 bits of information because only one segment has been added to each timeline. And so this is where the concept of MPD patching came from. And we really thought to ourselves, like, what if we could only send that new information to the client, right? How would you go about doing this? Well, again, we can't just infinitely burn money on the server side, right? The one way you could do this is to have the server remember everything the client has already been given. But then you need just dumpster trucks full of money, and unfortunately, I don't have the budget for that. Maybe Microsoft. Yeah? No? Apparently not there either. But instead, we wanted to pivot the problem and say, can we instead provide clients only what they need, but also have them do the work of remembering it? Use them as kind of a distributed storage and system. And so we created the patch manifest concept, and it's gone through a couple of iterations now, which is great. But it's a specialized server update response. So instead of getting the whole thing, you're only going to get what you don't already know. And so to start out a stream, of course, you need to learn the base state of the stream. Everything from the start of either the program or the start of the event until now. And so we're watching this great big buck bunny. Everyone loves it. Our initial join manifest is going to get us to a point in the stream. Suppose this was a live event. I don't know why you'd stream this as a live event, but suppose you did. And that manifest would also contain a link to the next update. And that link would contain a breadcrumb embedded by the server that says, hey, everything I've just put in this manifest is blah. It's whatever the server needs to understand what it's given you before. And so the client persists that into an in-memory form of the manifest, and every player has some form of this. I've not seen a player implementation that's just raw looking at XML as it's parsing or as it's running the playback clock, because that just doesn't make sense. But now what we're doing is we're separating the client's in-memory state from the networked state. And so when the client needs an update, it follows that link to get that update, and it gets a patch. And that patch is just that new piece of information. It takes that piece of information and puts it into its memory. But along with that patch, it gets an update where the server has added that additional information in. And so this continues on as time's going on. And so the client is building out this timeline, and the server is only giving it the updates that have occurred since the last update. And so to make this a bit more concrete, a join manifest looks very similar. The biggest difference, and if you saw the Mile High talk that I gave about this, you're seeing a lot of deja vu. This is, but there's a little bit of difference, and this is because we've modified the semantics as part of finalizing it in the dash spec. But instead of a location, it's a patch location. And the patch location is describing everything that's given to it. In this case, we're using publish time as kind of a base check, and we're using the last segment of it that was provided as the known state, assuming that you've gotten everything before. Because it doesn't actually matter how far in the past the client knows. It matters about the live head that they're looking at, what segment they know about. And then in addition, we've added this TTL attribute. And this is saying from this publish time until you add this publish plus TTL, this link is accurate and can be used. This is just to kind of head off some bad network actor state things that we've seen. But basically, if that TTL expires, you can go back and get a full manifest refresh. And it gets you back into the correct patching mode. So there's always a safe fallback in case something goes wrong. Now, when you follow that link, you get a patch. And a patch does not look like an MPD anymore. A patch is a simple thing. It describes the MPD it's being added to with the name of the ID. It also does some couple things here. It updates the publish time because you now know information up into the publish point. It gives you a new patch location, like I said, and then it extends the segment timeline. So instead of sending all of those nodes again, I've sent about 9. And that's about 1 kilobyte uncompressed. I could gzip it if I really wanted to. Wouldn't help much at that point. But it's about 2 milliseconds of parse time. And to give you an indication, even a 100 kilobyte manifest on certain streaming devices cannot be parsed and sustain 60 FPS playback. A 1 kilobyte manifest absolutely can. And the other part of this is it's solved the growth over time. So the updates are constant size scale, right? And this means it's efficient for the network, it's efficient for the client. There's a little bit of server processing overhead because it has to understand what's different. But that's an acceptable overhead. It's not remembering everything, it's just a minor addition to the output as a diffing component. But it's also keeping the server in full control of the timeline. So the client is not guessing when it doesn't need to, right? The server is still telling it where to go. And pulling in information from demux, like the stream remains cacheable, and we've extended this to also do add insertion because the server's in control of the timeline. The server can fork people out to unique experiences where it wants to, and then bring them back into consistent experiences. And you can see more about that in the demux presentation when the VOD events are out. But yeah, it's the interesting part here. I guess nope, no, wrong slide. The interesting part is that it's not obvious about the cacheability at first, but the idea is eventual consistency. Everyone joining the stream learns about everything that's happened, and therefore they're at the same live head point. And therefore, they're using the same query for the next information. And so they can all have the next same response. If someone falls out of sync, the next update will pull them up to date. Or if they fall too out of sync, they get the full manifest again and are back up to date. So you have the user, or you have all the clients pulling on the main head. And the thing we see is the latest 2 patches are usually what people are pulling. But there's very, very little variation. There's very, very little long tail, which is great. Like I said, we deploy this in production today. It's across every one of our devices except for one that doesn't run Dash. And it's actually in the Roku player. They have an implementation of this, and it works really well. And thank you to the folks at Roku for that. We have formalized this. We're formalizing this in MPEG. It is moved from the TUC. It's now in Amendment 1, and this is where that finalized specification patch form came from. You might, if you've been with Dash long enough, you might recognize it as the patch method that was for the in-segment patches. The main difference is a lot of people do not have their manifest processing at the same point they have their segment generation. So putting the manifest that describes the next segment in the previous segment is very, very difficult. And decoupling these out is just, it helps with the general scale and decoupling of systems. So we hope to see this landing in the 4th edition soon. To help people adopt and understand this, we're working within the -IF forum to provide reference implementations, but also provide interoperability guidelines. In particular, there's a larger task going forward of helping people do Dash well in scale. It's going to consider this. There's also a great proposal from Amazon, Amazon Video and Elemental, about the pattern effect and how to reduce the patterns in the manifest so that they can be compressed as well. But yeah, that's about how it goes. I hope it was interesting. Hope you learned some things. I can take some questions, of course, but yeah. I think Theodore had his hand first.
Yeah, when you say that, if you say that you maintain a reference version of the manifest that's used in case of like Denver errors and whatnot, does that mean you maintain a separate version for each unique stream or just a single reference? So your question is, when I say we have a reference manifest that you can fall back to, are we keeping that for each unique stream, or is it a single one, right? It is a single, well, it depends. So if you're doing add insertion, you do need to generate that back uniquely. But because you're separating out the join path versus the patch path, you can scale those services independently and have higher latency on that response of the join and still maintain a scaled system. Yeah, I was just wondering if there's a chance that someone might, have to rebuffer, seek back, and something there's a different add, like gaslight them by accident.
That would be really, really bad from a playout perspective, and that's something that you do not want to do, for sure. If you do add insertion, you need to make sure that fallback is a consistent update. Joey?
Do you have sample content available anywhere?
So, that is a problem because all of our content is DRM protected. No, but... Exactly. So I have a implementation in the -IF simulator. I'm, of course, building in the unit test and the corner cases at the moment. I'll be putting that back as a PR so that you can use that as a reference. At the same time, we'll also be providing the -JS implementation. There's a fun bug in that one I'm still working through. And we'll also look at other players and simulators as possible.
So you're saying the -JS implementation exists today?
It exists on this laptop, for sure. Both the live sim and the -JS will be pull requests back into the main repository after we've stabilized both sides. Cool. Well, thank you.
If anybody was at FOMS a couple of weeks ago, there was one of the discussion topics was actually all about test streams and the lack of test streams in different formats, and also one of the challenges of simulating a live stream, because obviously interesting things happen with live streams that may not happen with a VOD stream. So there was talk about that. I will post a link to the notes from that particular session on the video dev Slack.